Well, our Earth is a very special place. It's the only planet in our solar system or in our entire galaxy that we know of that has life. But Earth may not be alone. Astronomers have found, in the last 20 years, they've found thousands of planets orbiting stars other than the sun. We call these exoplanets. And there's compelling evidence that every star has a planetary system, and that as many as 1 in 10 stars like the sun may have an Earth-sized planet. I'm here to open the science session, because in studying other Earths and searching for them, we remind ourselves of some of the fundamentals, and we ultimately hope that by studying other planets that have much more diversity than our own planet, we can learn something that is helpful to us in the future. So before I get to the climate essentials for habitable world, I have a couple of slides on exoplanets to share with you some of the diversity of these other worlds. And I'm going to start with this animation clip that comes from software by NASA called Eyes on Exoplanets. It's showing us a real map of the sky. With the highlighted dots are stars with known planets. The white dots are stars that we don't know if they have planets or not yet. Here we're zooming into our solar system. Perhaps you could just dim the lights for a moment, and we can go in the software to any part on Earth. Here it's taking us to the west coast of North America, looking at the spring night sky, and this is what we'd see in the sky. We'd need binoculars, we'd need maybe a telescope, and there's one very special patch of the sky where NASA's Kepler Space Telescope stared for 4 years. Actually, the whole sky is covered with stars and exoplanets if we only had time to search every star. In this software, we could dial in a name of a star. Here, Kepler 186, and this software takes us to that star and will show us the orbits. This planetary system has 5 planets. And on the little menu there, you can get an approximate view of the habitable zone, the zone around the star where, as heated by the star, a planet would be not too hot, not too cold, but just right for life. We can zoom in a little farther, and here it's important to read that fine print that you can't see. Hypothetical visualization of planet. We don't have a way to study other planets outside our solar system in that level of detail. So actually, we can summarize the diversity of exoplanets by this plot that shows you planet size and orbital period. This is 1 Earth size here, up to 10 Earth sizes or more, and orbital period in days. Some planets have a year, an orbital period that's less than 1 day. Others have periods that are hundreds of thousands of days. Earth would be about here. We don't have any planets like Earth yet because our technology doesn't reach there. But I wanted you to appreciate the diversity of other worlds. Every dot here is another planet. Planets have an amazing variety of mass, size, and orbit. And as relevance for us here, we anticipate this will extend to exoplanet atmospheres, that a planet like Earth somewhere else could be born with a more massive atmosphere or with a different amount of carbon dioxide or other gases. So out of all those planets, and why we are here today, is about the so-called Goldilocks zone, the habitable zone. This cartoon here explains the concept, showing you this green zone with a planet where our Earth is, a distance from the star, that a thin atmosphere on a planet heated by a star will be not too hot, not too cold, but just right for life. And all life as we know it needs liquid water, so we're taking this habitable zone, habitable condition to mean a planet with surface temperatures that can maintain a liquid water ocean. Some planets are closer to the star, and they're receiving so much energy from the star that they'll be hot. Water vapor will reach the upper areas of the atmosphere where it would be photodissociated by starlight or sunlight, and hydrogen would escape to space with oxygen reacting with other molecules and surface minerals, thereby getting rid of the planet's oceans. We think that's what happened to Venus. And the outer edge here of the habitable zone, actually the gases that we're worried about, our greenhouse gases, would freeze out, water and carbon dioxide, making the planet too cold for liquid water and too cold for life as we know it. We think that's in part what happened to Mars. So now I'm going to turn to a few essentials of essentials for habitable worlds, starting with the so-called greenhouse gases. It's always astonishing to me to think how our Earth's atmosphere is 80% nitrogen by volume, 20% oxygen by volume, yet those gases play very little role in absorbing radiation. It's actually water vapor and carbon dioxide and other gases that we already know are very significant. Just like holding a sheet of paper can block more light than a clear pool of water. It's just really these small amounts of gases that are wreaking havoc. And in fact, in recent months at the Mauna Loa Observatory, they've been measuring more than 400 parts per million. And that's still a relatively small part overall, but for climate, it's important to note, which gases are strong absorbers. This plot here is showing you absorptivity of different gases. It's kind of an approximate plot, but it shows you how much sunlight reaches the surface depending on different gases. Here's our atmosphere kind of summed up. So 1 means no sunlight reaches the surface, and this is showing you our atmosphere and different gases. And here in the ultraviolet, ozone absorbs sunlight, so we don't get the harmful UV radiation at the surface. In the visible wavelengths, it's water vapor that's doing most of the absorption. And in the infrared, you can see the differences for these different gases. But in terms of a habitable climate, it's not just the inventory of gases, but their interplay. Pound for pound, adding more methane to our atmosphere has more of an effect than carbon dioxide, just because there's less of it. And it's not saturated in terms of its spectral features, which also are absorbing in some window regions. Water is an essential for a habitable world. It's the oceans, liquid water required for life as we know it, and we'll hear more about aquaplanets and oceans later from John Marshall. Here I'm showing you a cartoon of a water vapor cycle and just a photograph of water and clouds. So habitability requires surface liquid water. All life as we know it needs liquid water. But a sort of irony is water vapor, in part, actually large part, controls the surface temperature, which allows liquid water. And water has many other subtle but important roles in climate. Actually, it plays a role in convection, latent heat release when water vapor turns into clouds. Those and other factors affect the vertical temperature structure of the atmosphere, which affects surface temperature. Also, our atmosphere has a cold trap, preventing water vapor from getting to the upper reaches of our atmosphere, where it would otherwise be photodissociated with hydrogen escaping to space and our water going away. Finally, just want to mention that we actually, in thinking about exoplanets, have some of the similar problems, but at a different level of worry. And one of those have to do with water vapor. One of them is the relative range of relative humidity kind of allowed in atmospheres. Here on Earth, it's a concern for warming atmospheres and how much moisture can be held in the air, leading to bigger precipitation events. For other worlds, it's just simply a basic question of relative humidity and the factors that affect it. The next thing on my list are clouds. Not that they're essential to habitable worlds, but they actually still hold a puzzle to us for understanding radiation balance in our own atmosphere. We'll hear more on that a little bit later from Professor Dan Sitso. But actually, here it's every planet has clouds. Without detailed information, we are really at a loss as to how to predict how clouds form on other planets and how they evolve and their effect. But on Earth, water vapor, that very strong absorber, gets reflective for low, thick clouds. And the way that it traps heat and re-radiates depends on what type of cloud, how high its altitude, what it's composed of. And all of those things add quite a lot of complexity to climate on any planet. Also, clouds and aerosols and hazes that scatter radiation, what they do is they take information from one part of the atmosphere, imagine for a moment radiation being absorbed and re-radiated, and then scattering very long distances to another part of the atmosphere. This actually transfers information across large distances, really complicating the climate problem. My final item on my list for essentials for a habitable world is atmospheric dynamics. Now here, we already heard from our keynote speaker a mention of the massive snowstorm earlier this week, so local dynamics play a very important role as the climate changes. But for exoplanets and in a global sense, it's also important. It kind of forgives extremes in climate scenarios. Here I'm showing you a cartoon of a type of planet that we expect to be out there. Planets that are close to the star will be tidally locked. Their lowest energy state is such that they will rotate one time for one orbit. And so it's like our moon that shows the same face to Earth at all times. So what this means is that the planet will have one permanent day side that's permanently being heated by the star and one night side that's always in darkness. Now, do you think that one side would be just too hot and the other side so cold that the greenhouse gases would condense out? Well, actually, studies have shown, numerical simulations have shown that as long as the planet atmosphere is as massive as Mars's atmosphere, that atmospheric circulation will set up and transfer energy around the planet, keeping it basically habitable. Here at MIT, led by John Marshall's group and David Ferreira, we actually studied an aqua world at different obliquities. Exoplanets, other planets in our solar system, have different obliquities. So Earth is tilted 23 degrees, but what if it was tilted as much as 90 degrees? In this extreme, Earth's pole would be pointing towards the sun in a boiling daytime for a very long part of the season, and then it would be in nighttime for a lot of the season. What might you think happens there? It's way too complicated to summarize, but let's say that in this study we found that as long as the ocean is deep enough, the ocean will store heat in that hot summer and re-release it in winter, and there are a lot of complicated atmospheric dynamics that interplay with the ocean. And we'll hear more about the aqua worlds and ocean-atmosphere connection a bit later. So that was my summary of the climate essentials for habitable worlds. In the last few minutes of my talk, I'll return to exoplanets to tell you that when we hope to find and study planets like Earth in the future, we won't be getting spectacular images like this Apollo image of Earth. Instead, we'll be getting images like this. This is also a real image. It's taken by the Voyager 1 spacecraft at 4 billion miles away. And that's Earth just a point source. And it is sobering to think that if there are other civilizations out there in our galaxy looking back at us with the same kind of telescopes we're hoping to build, all they'll see is this pale blue dot. And all those intricacies of our climate will be lost to them. But nonetheless, we're still trying to glean out what kind of climate information about Earth could we see, imagining Earth from afar as an exoplanet. And here I show you some real data, Earth as an exoplanet through observed disk-integrated spectra. I'll just address a couple of these. This plot at the top is actually from Earthshine measurements, and it's showing you Earth's reflectance normalized to 1 at visible and near-infrared wavelengths. So if Earth had no atmosphere, this would be a straight line, just normalized to 1, ignoring surface effects. But what you see instead of a straight line are these big chunks taken out by water vapor, which is our dominant absorber at visible wavelengths. You can also see ozone and oxygen, and also Rayleigh scattering, which makes our sky blue and Earth look blue from afar. At the bottom plot, I'll skip to the bottom plot, showing you Earth's thermal emission. This was taken by the Mars Global Surveyor en route to Mars a while back. This should be Earth's thermal emission is a black body. It should be a curve going like this, but you see these big bites taken out of it by our strongly absorbing greenhouse gases. So in particular, carbon dioxide takes a huge chunk out at 15 microns, which goes to show, it helps illustrate the point about how absorptive and how strongly spectroscopically active carbon dioxide is. So just to finish up with a few more points, are there any habitable worlds out there besides Earth? Well, we don't know yet. We have thousands of known planets. A lot of Earth-sized planets are known, some planets in the habitable zone. We've studied dozens of atmospheres of hot giant planets, but we don't yet know if there are any other habitable worlds. Still, we love to speculate, and NASA has made some fun travel bureau posters. Kepler 186f, where the grass is always redder on the other side. That's the planet I showed at the beginning in the animation. Actually, it's around a red star, and people like to speculate what might happen with photosynthesis on such a planet. Experience the gravity of HD 40307G, a super-Earth. On this planet, it has about 1.5 times the surface gravity of Earth. This is the kind of questions we might ask our students on a general's exam. What happens to Earth's circulation if we change the size or gravity? Relax on Kepler 16b, the land of two suns, where your shadow always has company. We actually do have a number of planets orbiting a binary star. Imagine if they're out there trying to understand their climate. It's a lot more complex with two suns. So actually, you know, people love to say in the news, we must plan to leave Earth because we have a catastrophe brewing, whether that's climate change or other. But I can assure you that even though there are so many planets out there, space is vast. And those stars are just so far away, we really have no way to travel to them anytime in the near future. So our Earth is a very special place, and we must take care of it. Thank you.